Assalamu alaikum, this is Shakil Ahmed. In this tutorial, we will learn about statistical testing of hypotheses. First of all, we start with comparison of two population means. We have a data set on diastolic blood pressure. We just import the data set. I think this is DBP data set, and you can see the first few rows of your data, and you have uh, a variable treatment and diastolic blood pressure for 5 different time points, and the age of the patient and the sex of the patient. So this is your data set, and we just compute the difference between the DBP on time 5 and at the last time period to the first time period. So D80 is our data, and we add another variable in our data set DIFF, and which is the variable DBP5 minus the variable DBP1, and you can just compute this difference. And for making the assumptions of t-test, we just try with histogram. However, you can also make a probability plot, pp plot or qq plot for checking the assumption of normality. This data is almost normal. If data is not normal, we assume large sample size and continue with central limit theorem. So this is the histogram of difference, and this is nearly normal, not exactly normal, and we can just compare this difference for treatment A and treatment B using a box plot. Here the box plot is made for difference and for two different treatments, treatment A and treatment B. So we can compare the difference in diastolic blood pressure in two treatment groups. Uh, we can say this is control group and this is treatment group. In treatment group, the diastolic blood pressure is higher than the treatment group, or you can say treatment B causes in rise of uh, in a significant difference in uh, less significant difference in diastolic blood pressure as compared to treatment A. I think treatment A is more powerful as it reduces the diastolic blood pressure for the 5 time points. So you can just compare the difference in diastolic blood pressure for the two groups, and then we apply the t-test for this difference for the two treatments. Our null hypothesis is that the the mean of the difference is same for the two groups, and we are assuming that the variances are equal, population variances are equal in two groups, and just see the result. You have t statistics, and the degree of freedom is 38, which is 40 minus 2, and p value is uh, 0.000, which is almost 0. So we have uh, we can conclude that there is a significant difference between the difference in diastolic blood pressure on two different uh, for the treatment A and treatment B, and we can see the confidence interval for this difference, and the difference mean of the differences in two groups are minus 15.5. This is for treatment A and this is for treatment B. Similarly, we can conduct same test uh, without assuming the equal variance in two groups, and you will see again a significant difference between the two treatment means, and you can test for the equality of variance, whether the two variances are equal or not. Uh, just check about the homogeneity of variance test, and the f value is 1.5 and the p value is greater than 0.05. So the two population variances are the true ratio of variances is not equal to 1. That was our alternative hypothesis, and our alternative hypothesis is not accepted, and our null hypothesis is accepted, and we conclude that the two variances are equal as the ratio of variances are close to 1. And we can conduct a non-parametric test to test the difference. This is the Wilcoxon sign rank test, and it also give W value 0 and P value is almost negligible. It also uh, conclude or suggest that the two population mean of differences are not equal in the two groups, and you can find difference for the two groups using this command. Here you are specifying treatment A. Basically you are extracting the difference for treatment A and the difference for treatment B, and we have two variables, and then just apply t-test, uh, and the alternative hypothesis here is that mu A is less than mu B. So just check the result. We again conclude that our null hypothesis is rejected, and we conclude that what was our alternative hypothesis? Our alternative hypothesis was that two differences in mean is less than 0. So it is accepted, and the null hypothesis is rejected. So the uh, mean difference in treatment A is less than mean difference in treatment B. And now we aggregate our data using a data frame command. Basically, we want to conduct analysis of variance to check whether the mean diastolic blood pressure is same for all time points. We have 5 different time points: T1, T2, T3, T4, T5. So I assign number 1 to time 1 and 2 to time 2 and 5 to time 5, and then I again add the treatment variable as 0 and 1. You can just see your data, and DAT, for example, I just want to see this. Here we have diastolic blood pressure for 5 different time points. So we are just writing the DVP1 first, and then when DVP values are ended, we just start DVP2 and then DVP3. Uh, in this way, we have first 40 values for DBP1, and then 40 to 80 we have DBP2, and the 80 to 120 we have DBP3. Uh, in this way we have total 200 values, and our data set is now uh, of size 200 instead of size 40. And similarly, we can write the treatment A as 0 and treatment B as 1. Then uh, first 20 values are assigned to treatment A, and remaining 20 values are assigned to treatment B. So I just write for each time points. I write repeat 0 for 20 times and 1 for 20 times for this 40 observation. Similarly, for this 40 observation, I again repeated 0 20 times and 1 20 times, and so on. So in this way we have a data set of diastolic blood pressure. I called it X variable, and the time variable and the treatment variable. So we have 200 observation now, because we have 40 observation for 1 dBp, and we have 5 different time points. In this way we got a data set of consisting 200 values, and the time is repeated for different time points, 1 for time point 1, and 2 for time point 2, and 5 for time point 5. And the two treatments are assigned values 0 and 1 for treatment A and treatment B respectively. So in this way we have a data set, uh, new data set DAT, capital DAT, and we can see we can convert the time and treatment to factor using as dot factor command, because while applying in our qualitative variable on which we are making groups should be a factor. So time is a factor here, and the treatment is also a factor here. We have two factors. So we start with one Way Anova, and just use the AOV command and your dependent variable and the independent variable and the data set. So just run this command, and you will have the summary of your result, your test. This is your analysis of variance table, and there are two factors, time and residual, the degrees of freedoms and the sum of squares and the mean squares and the f value and the p value. Here we can see that the mean for the uh, 5 different time points are not equal. Our h naught is rejected, as the p value is much smaller. So when h naught is rejected, we conclude that the means are not equal, but we don't know which pair of means are not equal and which pair of means are equal. For this purpose, we use Tucky honestly significant different test, which compare means pairwise. It will compare mean of first time point to second time point, and the first time point to third time point, and so on. So just apply the Tucky honestly significant different test to the test you already applied. Uh, this is called post hoc test, and we have following combinations. Here we have 5 time points: time 2 to time 1, time 3 to time 1, time 4 to time 1. These are the differences between the mean, and this is the lower confidence interval limit for the difference, and this is upper confidence limit for the difference, and this is the p-value. And p-value suggests that which uh, pairs are significantly different and which pairs are significantly not different. So we see that a pair 2 and 1, the diastolic blood pressure at time 2 and time 1 is even significantly different at uh, alpha 0.05, but if we take alpha is equal to 0.01, it will be not rejected, and we say that the two means are not equal. uh, and we just say that the mean diastolic blood pressure, the mean difference in diastolic blood pressure uh, for time 3 and time 2 is same as the p-value is larger than 0.05. So this is the post hoc test for analysis of variance, for checking the means of several population or several groups. Similarly, we can conduct a two-way ANOVA with interaction. We have the dependent variable and we have two independent variables, treatment and time. The steric here stands for the interaction term. So we just start model 2 and the with the ANOVA option and just run this test and see the summary. We have two factors, treatment, time, and then interaction. In this way, we have three different source of variations and the residual, which is within sum of square. These are the degrees of freedom, and these are the sum of squares, and these are the mean squares, and these are the f value. And there are three f values: one for treatment, one for time, and other for treatment and time. There is an interaction between treatment and time. So these are all significantly different. So the treatment means are not equal, and the time means are not equal, and there is a significant difference between treatment and time. So we just make a plot for interaction plot. Just use the power function. mf row means we are making two plots and with first row and second row, and these are the uh, margins, and we have a data set, and the interaction plot is the command, and we have three variables: time, treatment, and x is our dependent variable, and the two time and treatment are independent variables, and we are just setting legend is equal to true. So I didn't run the command power function, so I will just run and uh, run these two types of plots. So I have legends as well. This is for treatment, the two treatments, and this is time, and this is diastolic blood pressure, and this is diastolic blood pressure, and this is treatment, and this is time. So I just change the position of treatment and time here in these two plots, and you can see is there any interaction between time and treatment for diastolic blood pressure. And finally, we again uh, use the Turkish honestly significant difference to assess the differences in mean for columns and rows. Here we have many combinations, as we have one treatment and one uh, control group and one treatment group. So we have basically two portions for this. Uh, we started with uh, time. For time, we have just this HSD values. These are the differences as we already explained in above one way Anova. And for treatment and time, this is for the interaction. This is just for treatment, and this is for time, and this is for the interaction of time and treatment. So the last one has many options. Basically, for example, we are checking the difference between the treatment group or treatment B and time point 1, and treatment A and time point 1, and we are checking the difference between treatment uh, A and time point 2 and treatment A time point 1, and so on. So we have many possibilities for the interaction between the uh, interaction means. So these are all about one way and two way ANOVA, and we can also test the uh, proportion for different categories. We have different proportions. Then we use chi-square test by using by comparing the expected frequencies with the observed frequencies. We have the number of observations in each group, and these are the probabilities of falling each value in these groups, and these are the observed values for each group. So we just run this command and then apply proportion test. Basically we are comparing proportion in different groups, and we can say that the chi-square value is 57.79, and the degree of freedom is equal to 3, and the p-value is 1.7 ki power minus 12, which is almost 0. So the four proportions are not equal, and we reject our null hypothesis, and these are the estimated proportions or the sample proportions. So these are all about testing of hypothesis. If we have time, I try to make some more video on testing of hypothesis related to regression analysis and non-parametric testing. So for now, thank you, and practice with your own data. Good luck.